We're going to be looking at perception, how we look at things, and patterns, which are the things that happen within perception, where we make patterns. And I'm going to start by telling you a very important story, and if you remember this story for the rest of your lives, it'll do you a lot of good. And it's a true story, which happened to me years ago when I was at Oxford, and in those days you had to be back in your college by midnight, otherwise they closed the gates and you had to find your own way in. Well, on my first night there, I was going off to a party in London, so I asked one of the old hands who'd been there before how to get back in. And he said, it's very simple. You go along, you come to a wall, you climb it, you come to a second wall, you climb that, and you find yourself inside. Well, I came back to about 2:30 in the morning, and you have to approach from this direction because there's a police station somewhere down here. And I came up to the wall, and I climbed it, and I went along, and I came to the second wall, and I climbed the second wall, and I found myself out in the street again. I then went all the way back, climbed the wall, went along, found another wall, and this time I thought I'd explore, which I did, found a gate which offered much easier footholds to climb, got to the top of the gate, and I was sitting astride the top of the gate when the gate swung open. It had never been closed. Eventually I got in, and that's since become a classic tale of idiocy, which has been told back to me on 2 occasions, people forgetting that I was somewhat involved. Now, the purpose of the story really is to illustrate a very important point in thinking, which is this, which is that excellence in wall climbing does not itself mean that you're climbing the right wall. And in thinking, if we divide thinking into 2 stages, we can look at what we might call the perception part of thinking, how we look at things, and then the processing part of thinking, which is what we do about them once we've looked at them. So climbing the wall is processing, perception is deciding that's the right wall to climb. Now, quite often in thinking we put all the emphasis on the processing, but I think that in general, most of the important part of thinking takes place in the perception area. And that's what we're going to be looking at today. What happens in perception, how we look at the world, how we generate our ideas about it. Let me ask you a question. That's a noughts and crosses game area, and we'll just put a square around it for the moment. So it's 9 squares. Suppose I start in any square, and I move to any square next. Just give me an idea how many possible routes, how many possible ways might there be of going through that noughts and crosses grid. I'm going to ask you for suggestions. How about you? Just guess. 4. Gentleman behind.
Several hundred.
Several hundred. All right, anyone?
27.
27. Well, as far as I know, and I could well be wrong, the number is something like 362,880. Because you multiply 9 by 8, by 7, by 6, by 5, by 4. Now, some time ago, some years ago, I invented a little jigsaw puzzle, which had only 16 little square pieces. And what you had to do was to arrange these to make a big square, which was 4 by 4. But there was a catch in it. It was so designed that you couldn't tell you'd got the right answer until you'd placed every piece in the right position. So you had to try out trial and error. Now, with trial and error, even if you put one piece every second, day and night, without stopping to eat, drink, or sleep, in order to be sure of solving it, it would take you, as far as I calculated, but that's open to question, it would take you more than 1,000 million years to solve this simple jigsaw. And since man's only been on Earth in any form for 10 million, and even the termites for only 100 million, it's something you give to your enemies for Christmas. Now, the reason I mention these is that the mathematics of combination are huge. And if we had to try and cross the road, by standing at the side of the road and really analyzing all the information that came towards us, it would take us about a month just to cross the road, as we analyzed all the data. But we don't take a month to cross the road. We cross the road in very normal time, a minute or 30 seconds, 20 seconds. The reason we do that is that the brain is designed to be brilliantly uncreative. That is the main purpose of the brain, to be brilliantly uncreative. The main purpose of the brain is to take in all the information and as quickly as possible put it together to give a pattern. And once we have the pattern in future, let's put the pattern down here. It's like a track or road. In future, once we have the pattern, all we need to do is just recognize the beginning of the pattern, not analyze anything else, just read out the rest of the data. It's a wonderful system for making sense of the world and allowing us to operate on it. Whereas if we were working in these sort of figures, we'd never be able to cross the road. So the brain operates to make patterns and then use them on every possible occasion. And if something is even remotely similar to the pattern, then we will treat it as if it was that particular pattern. So it's a wonderful device for allowing information to organize itself into patterns. We recognize the pattern, and then we go on to the next pattern, and we go on to the next. It's rather like with the Rubik Cube, which some people are very good at doing. And one of the ways to do it is you recognize the pattern you get, and then you know what to do next. That produces another pattern. You recognize that, and you go on, and you go on. Anyone here who's a whiz at doing the Rubik Cube? All right, Dinah, will you give the gentleman the Rubik Cube? There we are. Now you start off with it. Okay, we'll come back to it a bit later. Now, in making these patterns, the brain is very different from a computer. Totally different from the way a computer works. Let's contrast the way the brain works with a computer in a sense. Imagine we've got a tray, and the tray is full of sand. And what we do is we drop a ball, a steel ball, on the sand. And it gets embedded in the sand where we've dropped it. In other words, it stays exactly where we've dropped it. The sand will give us an accurate record of what we've done. This is a passive surface because the ball will stay exactly where we've dropped it. We drop it here, the ball will stay here. Most of our information systems are of that type. But let's contrast that with another type of system. And in this other type of system, the surface is shaped like this. Imagine a plastic surface shaped like that. Now, no matter where we drop the ball on this surface, it will always end up in this same position. If we drop it here, it will roll along. If we drop it here, it will roll along. So no matter where we drop it, it's moved to this position. This is now an active surface because it actually changes the information. In a sense, it curves the information. Now let's move to the next one, the next type of system. And the next type of system, we have a tray. And this time we've got heavy oil or treacle or molasses in there and a rubber membrane on top. And we drop the first ball on it, and the first ball sinks in gradually into the molasses or treacle. It then shapes the surface like that, so when we drop any other ball there, it rolls down and ends up near the first one. So this is similar to this surface in that the information is altered as it's received, but there's a difference that here the shape is determined by some outsider. Here the shape is determined by the information that comes in. So let's move on to another pair of models which show this even more clearly.